Yeah, I think you might have to start again. I'm so sorry.
No, it's not your fault. It's trying to do too many things at once. So verify, Melissa, when you have live stream again.
Did you get the link? Verify people on the stream.
Can you put the live stream here so I can see if it's running or not? Just log into the live stream on a browser here.
Got the link, and then I will send it.
That's not you.
No, I know, but I sent the link from the computer.
Okay, I see live stream.
Yeah.
Okay, will we be able to run like that? Okay, I guess I don't need to see it. That's just too dangerous.
Well, it's okay.
Well, did you close it?
I wasn't going to close it.
If I can't see it, it's not worth having up. So either leave it up or... Okay, how's the audio, Melissa, on your end?
Good.
Okay, guys. All right, take 10 on the live stream. So, going to back up yet again. We're talking about the wave nature of particles. And we saw particles do behave like waves, and we are going to assign them wave functions. And the wave functions will have a wavelength momentum relationship. And these are real particles. So they have a real mass. Mass times velocity is the momentum. That momentum is related to the wavelength of the particle. So when a particle behaves like a wave, that wavelength can be calculated from its momentum, from its mass and its velocity. So it's a strange property for matter to have a wave-like nature, but we can calculate a real momentum, mass times velocity, put that into this equation and get a wavelength. So the duality between particles and waves holds for matter, and we've seen that it holds for electromagnetic radiation, for light. Light behaves like particles in that there are photons, chunks of energy, discrete chunks coming along the wave, and they can deliver their momentum, their energy as particles in bits. And we saw that in the photoelectric effect. You deliver a bit of photon energy, it ejects an electron. So matter and waves both behave with this duality. And this wavelength that you calculate is called the deBroglie wavelength. So this wavelength here, related to the momentum, is called the deBroglie wavelength. And both particles and waves will have a deBroglie wavelength. If you're manifestly a wave like light, then your deBroglie wavelength is your wavelength. So a yellow photon, so we're calling it a photon because it's the packet of energy, the particle of light with energy h times nu. And energy h times nu is a packet of energy. That packet of energy has a de Broglie wavelength 600 nanometers. That corresponds to yellow light. Electrons now. So electrons traveling quite fast, 10,000 or more meters per second. That's 10 to the fifth, 100,000 meters per second. They have a de Broglie wavelength of 6 nanometers. Now, I'm talking nanometers here. So 10 to the minus 9 meters. So the de Broglie wavelength of an electron is 6 times 10 to the minus 9 meters. It's on the order of nanometers. So it's on the order of the size of atoms and molecules. So an incredibly small wavelength. It has that wavelength, though, that just starts to be detectable. That is, we could do that diffraction experiment and see electron waves interfering with each other. So it's a detectable wavelength, but a very small one. Go to sodium atoms. So now this is more massive. As you know, sodium, hundreds of thousands of times more massive than not hundreds of thousands of times, tens of thousands of times more massive than an electron. If it's traveling at 300 meters per second, it has a measurable de Broglie wavelength. So now I'm at 600ths of a nanometer, but believe it or not, that's still something you could detect or you could register in certain kinds of experiments. If you get to something macroscopic, like a baseball, traveling at 40 meters per second, that's a very fast, yeah, if you got an arm and you can throw 40 meters a second, call the the baseball league, because that's a wicked fastball. But even if you can throw it that fast, it has a de Broglie wavelength 10 to the minus 26, and we're already at nanometers. So 10 to the minus 26 nanometers, so practically undetectable. And I shouldn't say the word practically, like, but what I mean is there's no practical means, there's no means in the universe that we know of to detect a wavelength that small. So we have this particle wave nature of matter, but it only applies to tiny matter. You could say, well, all matter has this wavelength, but macroscopic matter, the wavelength is so small, it has no effect on our reality, on the physics that we understand. So let's look at a neat historical note. I do hardly any historical notes in Chem 1. And in fact, when we assign reading, or you'll see that we're going to use this Prism software, we'll try to give you a demo on that later. We try to remove historical stuff from chemistry. That is, how did people discover things? And we do that not because it's not interesting. It's actually fascinating. I love to read about how these things were actually discovered. And we talk with the photoelectric effect, and the progress of science isn't very linear. It's up and down and all over the place. And science is being done by different people. And so back in the day, 1925, de Broglie had just proposed that matter could have wavelengths. And he was a physicist doing it on his own. In Germany, Davidson and Germer were working on an experiment where they were shooting a beam of electrons, which we'd just gotten the capability to shoot beams of electrons. So people were playing with them. And they were shooting them at graphite and metallic crystals. And they noticed diffraction patterns. And they couldn't figure out what was going on. Why do I get a diffraction pattern when I'm shooting particles? Why do they appear to be interfering with each other like a wave? So they go, well, I don't get it, but here's an actual, and you can read this in your notes. You might not be able to read it here, but I'm just going to read this to you because it's amazing what they did. So they're doing this investigation. This says this investigation was begun as a result of an accident which occurred in this laboratory April 1925. And we must admit the results proved to be quite in variance with our expectations. Nobody says nobody says quite in variance with our expectations anymore. That means we didn't know what the heck was going on. The most striking characteristic of electrons' beam scattered through a single crystal of nickel being a one-to-one correspondence to the beams that would have been found if the same crystal beam had been incident beam of X-rays. So they're going, we've done this experiment with X-rays. We shot X-rays at this crystal and we got waves, but we understood we'd get an interference pattern. Then they shot a beam of electrons, got the same interference pattern. And they said, that's matter. But they said, look, the interpolation involves association of a wavelength with the electron beam. And this wavelength turns out to be in agreement with the value h over momentum predicted by deBroglie. So this, David Germer writing down in his notebook when this happened and realizing, holy crap, deBroglie is right. Particles can have wave nature. So that's an exciting bit of science, and this is so awesome that you have that little excerpt in his own handwriting where he's saying stuff like, the results proved to be quite in variance with our expectations. That's kind of worth reading that. So a little bit of history there. Let's do a experiment which actually has some history. One of our Berkeley Associated Nobel laureates, Steve Chu, laser cooling of sodium atoms. So here's the question. How many photons are needed to approximately stop a sodium atom traveling, as we said in the last slide, at 300 meters per second? How many yellow photons do we need to stop that? So here's the sodium atom, and here's the photon. Photon has particulate nature H nu. Sodium obviously has particulate nature. Those two things collide. How many photons to approximately bring that sodium atom to a stop? I can leave that there. Did you start the poll? Okay, we'll bring up the group of 4 here. I'm going to leave. They're watching the live stream still, right?
Yes.
So they can see this. So here's the information you need to do that. A sodium atom, and its deBroglie wavelength, the yellow photon wavelength. Think about that for a minute. Can you mute me? Okay, you guys can vote on this one. You've discussed it for a minute, but the iClicker wasn't running. So go ahead and vote now. We'll go into the breakout rooms quickly on this. Just give it a quick thought. You had a little time, but you might not have been able to see the Chem Quiz. We didn't send the screen capture to you, I don't think. Yeah, but not. No, don't worry. This has been a heck of a morning already. I'm amazed you got that up ready to go. That was fast thinking. Okay, Ryan, there's approximately 100 people. Let's see what you're thinking on this one. B and C are popular. So let's talk about it. Let's go into breakout rooms. I'll join, and the GSIs will join, and we will see what you're thinking. You now, well, you can go ahead and start the poll again, and at this point, you can advance your PowerPoint, right? 1, and they should see the group of 4. Okay, and that's going out on the live stream. All right, you can mute me. I will talk. Hey guys, this one of our more challenging chem quizzes so far, not really because of the chemistry so much, in that there's a little bit of physics coming in that you might not have been aware of, so we'll just chat about it briefly. But why don't you push a button so we can get around 100 responses, and we will have a look at and talk about this one.
I think some people are having trouble. We're gonna.
With the iClicker?
Yeah, we're gonna open and close it after this poll. So.
Okay, so let's see. Yeah, we're only getting 86. So let's see what this vote was. We'll see what you have voting here. So now we're moving towards C. So I believe I agree with you. I can't remember what the answers were off the top of my head. So let's advance. So the answers were about 1 photon, about 100 photons, about 10,000 photons of light. So what you had to consider here, and this is the part where I didn't really expect you to know everything that was going on. I wanted to just get the juices flowing. But you have a particle, a real particle here with a momentum, and you have a wave coming in that also has a momentum associated with it now. So if they had the same momentum, a sodium atom would come in here, and a particle of light, a photon of light with the same momentum, would hit it and stop it. Now, they don't have the same momentum, and we can see that from our deBroglie wavelengths. The sodium atom momentum is 0.06, the photon momentum 600. So those are off by a factor of 10,000. Now those wavelengths are off by a factor of 10,000, but the wavelength and the momentum are directly related to each other, we know now. So the momentum of this particle is h over its wavelength. Same for this, is h over its wavelength. So these much, much smaller momentum, but if I could take 10,000 of them, then that would be these two momenta would be equal. So we have 10,000 of those guys striking the sodium atom, and that would stop it. And as with all chem quizzes, you're not supposed to get them right, or we don't grade them. This isn't about getting the right answer. This is about talking about it with people in the class, with the GSIs, and me when I can join your groups. It's about a discussion. And it's about taking a break so you don't have to listen to me talk so much, and you can talk amongst yourselves. This is also a Nobel Prize winning experiment. So remember, the momentum of a particle, its motion is related to its temperature. Motion in a system is a measure of its temperature. If you can bring these almost to a stop, you're dropping the temperature. So some of the coldest temperatures ever achieved were by laser cooling of atomized atoms at low pressure in the gas phase. And that was done by Steve Chu. He's now at Stanford. You might recognize his name. He was also the Secretary of Energy under President Obama. That's when we had smart people running the country. We had a Nobel Prize winner as our Secretary of Energy. So that experiment, laser cooling of atoms, good enough for a Nobel Prize, and very, very, very close to absolute zero. Absolute zero, zero on the Kelvin scale, is when matter stops moving altogether. And you come within a few tenths of a degree of that in this experiment. So this one, a little bit more straightforward. Electrons with lambda around 4 nanometers are heated to 4 times their kinetic energy. So they're heated up, their kinetic energy, 1/2 mv squared, increases by a factor of 4. Kinetic energy can also be cast in terms of the momentum, just putting momentum as m times v. So you can write the kinetic energy either way. We heat up those electrons. They're going to go faster, more kinetic energy, higher temperature. What is the new lambda? So you're going to go from 4 to a new lambda after that heating occurs. So we'll start the poll and see if there are any people registering a vote. They might not even have heard it yet. There's a webcast delay. Okay. Votes are coming in.
Question.
Am I on? I can stay on.
No, like a chemistry question.
Yeah, go ahead. I can answer.
When they were stopping the motion of the atoms, how did they make sure that the velocities of the photons and the velocities of the atoms were opposite each other?
Oh, clever. The direction. Yeah. There's been a question. It's a good one. I'm just going to put it off till we're done with the Chem Quiz, so you guys can talk. I can go. Okay, let's see what you're thinking on that one. So B is the most popular. Can you quickly show us the Chem Quiz again, Ryan, so we can see what B is? I think you can go. B, you say a factor of 2 in the wavelength. So it went from 4 nanometers to 2 nanometers. I agree with you on this. We won't do a discussion again, and I'm sure you kind of discussed already. You can stop that poll, Ryan, and I'll take over the screen again. So you guys are saying that the electron comes in with a kinetic energy that is known from its wavelength. The mass isn't going to change, so the kinetic energy is proportional to its momentum squared. And all we're saying is we made that go up by a factor of 4. So in order to get 4 times the momentum, in order to get, 4 times the kinetic energy, you would double the momentum, 2 times P, because you're going to square that whole quantity. So that a factor of 2 here would give you a factor of 4 in kinetic energy. So that squared relationship shows up. You have the momentum increased by a factor of 2. The wavelength goes down by a factor of 2, and you understood that that went to 2 nanometers wavelength. So interesting question. While you were in the discussion there, the question was, if you have those sodium atoms coming in from one direction and you have photons coming in from the other direction, how do I make sure that they hit each other so that you do get that correct transfer of momentum? And the answer is, the simplest answer that is close to correct is you do this in a laser cavity. And in the laser cavity, you have coherent and transverse light. And when you have that coherent and transverse light, you can, in the presence of a crystal, a cavity low pressure sodium, then you can ensure that you have photons going all in the same direction. Now, the sodium atoms, you can also get them going mostly in the same direction if you have a beam of sodium atoms, or if you have sodium atoms that are very, very, very low in temperature to start with. So very diffuse and not very many of them. So the ones that you hit can come to a stop, and or the ones that you hit can slow, and overall, the sodium atoms coming at you in general slow down. So you don't stop any of them, but you stop the momentum of the particles in this direction, and that's enough to start dropping the temperature, mainly because you get to such low pressures of sodium to start with that you have very low numbers of particles. So the short answer is you really can kind of point the beam in the right direction, and then you rely on the fact that you don't have to stop too many sodium atoms coming in the other direction. You can also have lasers coming in from different angles. So let's go. So let's continue. We'll talk about standing waves now. So we understand that matter has wave-like properties. Waves we understand pretty well. We were talking about those. So we can apply the properties of waves, essentially ocean waves, light waves, just general properties, sound waves. We can apply these macroscopic properties of waves to matter, because we said matter has wave-like properties. If we apply those properties of waves, what do waves do? Well, we know waves interfere. That's how we decided that matter had waves to start with. So what other properties of waves will matter show us? And it turns out some very interesting ones. This is where quantum mechanics comes from, originally called wave mechanics, because as soon as we decided when Germer and others did that experiment and said, oh, I can show electrons behave like waves, everybody jumped on the bandwagon and said, we know how waves behave. If the electron's acting like a wave in that experiment, is it going to act like a wave in other experiments? And heck yes, it did. And a whole field of physics was born. So let's just look at some of the simple properties of waves. We don't even have to talk about complicated quantum mechanics right now. We just say, well, we know how waves behave. Will matter do the same thing? So we can think about it macroscopically and say, can we detect that microscopically in the system? Question?
Does all matter have wave-like properties?
So the question is, does all matter have wave-like properties? And the answer is yes, but it doesn't matter for most of matter. So that is, we saw in the table of deBroglie wavelengths, and you could probably bring that up really fast, Ryan, if you could go to that slide and I can go to your screen. You have to go back into the lecture to the table. Can you go just to the table? It's probably at the beginning of the lecture. Yeah, that one. Okay. Ryan's brought up that table for us. It's a good question, so we'll just have a look back at that table. So the answer is yes, we decided we can apply the principle of the deBroglie wavelength. We can say the wavelength is Planck's constant over the momentum, but things that have big momentum, that wavelength essentially goes to zero. So macroscopic things, you could say they have the wavelength. It doesn't matter. It's just too small for an experiment to detect. This is practically no effect. That is, there's no experiment we can do to detect that. These tiny particles, we can detect those wavelengths. So wave mechanics is the science of the tiny. It applies to tiny things. Because, of course, that deBroglie relationship. But if these tiny things are behaving like waves, let's remind ourselves of some of properties of waves. So we can imagine a system for a minute. So let's say there's a bead, some particle, and it's moving back and forth on a string, and the string's tightly bound, so it stays essentially in one dimension, goes back and forth along the string. If it behaves like a wave, now, if it's just going back and forth on the string, it's behaving like a particle. But we could say, well, what if it's incredibly tiny and it has wave-like properties as well? If it did, then there'd be some wave function associated with it. And this lambda, we know how to get now. This wavelength, we understand where that comes from, the momentum of the particle. And these waves are easy to cast on a string. If we know the length of the string, we can say, well, I know the length of that string, and I know the relationship of the wavelength to the momentum. So if I have a fixed length of string, how do those things interact? How does that wavelength and that length of string interact with each other? Well, it turns out it's a standing wave. We talked about standing waves earlier. You can have traveling waves, and you can have waves that stay in one place and just go up and down. And this is what I've drawn here, waves going up and down along a string or in a system of length L. So you have a system of length L. This is one of the standing waves. Here's another standing wave, and here's another standing wave. Now, to get standing waves, you have to go to 0 at both the start of the string and the end of the string. So not all waves work. You can't have all willy-nilly wavelengths in there. You can have a half of a wavelength, because that's 0 and 0. You can have a full wavelength. You can have 1.5 wavelengths along that, because those all have 0 at both ends. So a feature of our particular wave function that we're looking at is it's got to be 0 at both ends. So if I put 0 in here, I have to get 0. And if I put L in here, I have to get 0 for the value of X. But you can see, well, those are just half wavelength intervals. Half wavelength intervals, if I apply that to L, then I can get a relationship between the wavelength and the length of the box, or length of the string. And I can see this interesting property. Not one wavelength works, but all wavelengths that have this kind of relationship, 2L over n, where n is an integer. So here n is 1, n is 2, n is 3, and I have n pi over 2. Those are wavelengths that are working. And this is what we call quantization. It's a really simple thing. It's just this, wavelengths standing along a string. Not all wavelengths work, but multiples, integer multiples of half wavelengths work. And those integer multiples, we end up calling quantum numbers. And we can show you that in a couple ways. So sound is a wave. So if sound is a longitudinal wave, but if I take a fixed length of tube where the sound wave has to be stopping here and stopping here, so a fixed length, then I should have fixed wavelengths. Only certain wavelengths are going to work and stand along this tube. So only certain standing sound waves will work in this tube. That means waves of sound are tones. You recognize that. So this tube, when I play this tube, I can't do all the notes continuously. I can't do, I can only do steps. So let's actually hear that. See if I can make it loud enough for my mic to pick it up. The whirly tube broke. Well, now it's a different length. It's a different length, but it's much harder for me to get it going fast enough. So is that coming up on the mic? Can you hear that? It's coming up on the mic. I got only certain wavelengths here standing in this tube, even broken. Melissa, we're gonna try and show you on a real piece of string, and we're not sure we can do this. What does the shot look out? Do you have to pan out? Did I give you the remote? So Melissa and I are gonna try and get standing waves on this string. So I am gonna add energy to the string. Just at one tension, Melissa, and I'll do the rest. So there is a standing wave, one full standing wave on that string. Does that look okay? And I can also get half a wave, probably. That's easier to get. That's just a jump rope. There's half a wavelength, and I got 2 full wavelength. And Melissa, can you point? I'll try to do it. Right in the middle. That's okay. Right in the middle. That's one. I'm getting too tired. Can you give me a little more tension? Just go that way a little bit more. I'm trying to get back to, there it is. Right in the center, you see the string isn't moving.
Right there.
Right in the center. So that's what we call a node in the wavelength. It crosses 0, and there's no motion there, even though there's wild, crazy motion elsewhere. Thanks, Melissa. So there's, and Ryan for the finger. They're the nice kind of finger. So she showed us where the node was in the string. So I hope I can show you this. Oh, it's going to load again. Don't load again. Oh, wait, how do I go to this? No, don't show me that. Show me that. Oh, poopy. It's going to go through its long loading process. I tried to have it ready in advance. You will get the link. It will be posted. I want to see if I can get this one to go, because it is kind of crucial to what we want to do moving forward. So it is initializing the graphics. We'll just give it a second to start. We had this started up in advance, and I think what we'll probably do is we'll start them on the other computer, because maybe they'll stay running. But as soon as I went back to this, it restarted the whole browser. Come on.
There's a question while we're waiting.
What's the question? There's a question.
Can you talk about what n represents in the equation?
So the question is, what does n represent in the equation? And a very simple thing. It was just, we saw that half wavelengths, every multiple of 1/2 wavelength, gave us another way, another mode for a wave to stand in that, along that string. So it's just counting. N equals 1, half a wavelength. N equals 2, 2 times half a wavelength, or 1 full wavelength. And 3 times half a wavelength, or 1.5 wavelengths. It's just a counting number. It's counting the various modes. And I can see them here. So here I can look at the wave that fits in this box. So this is the length of our string. It's the purple line. And the lowest energy one looks like what we saw, 1/2 wavelength. We can go up. Oh, no. Oh, poopy. Oh, well, I got a little help there. That worked. Maybe it's just a little slow. There we go. So here's our first energy level. Now that's n equals 1. Oh, darn it. Let's see here. Probability, real part, imaginary part, particle, mass. So this screen is not allowing me to choose the various energy states. I can move these, but I can't click on a individual wave, even if I get them farther apart. Well, poo. You guys can play with this. The green lines are the energy levels, and when you play with it, you can just click on them, and it will show you the various wavelengths. It's I think it's just the screen isn't touch sensitive enough for me to activate an energy level. And look, if I did, you would see on the first energy level, first green line, I see one half standing wave. If I go up one, I would go to a full standing wave, and then up one more, I'd go to 1.5, which is essentially the picture I drew in the other. This is nice because, well, we can show one nice property that as your string gets longer, we saw that, I can change this. And look at, as the string gets longer, these green lines pack in more densely. So the energy levels become closer together. And we know that because it's related to the wavelength. Those half wavelengths become shorter, and we can have more of them fit in. And the more that fit in, that corresponds to, you saw Melissa and I doing it, I had to shake very hard to get a full wave. I'd have to shake even harder to get 1.5 waves. And that's the energy I'm having to put into the system. 1.5 waves is higher energy than just the half wave. And that's reflected here. The length of the rope from here to here would show us that. Where am I? I'm here. So disappointing demo. I'm going to have to, we'll have to run them on the other screen. The screen isn't sensitive enough for me to do these things. So we've gone to a wave function for a piece of string, but if it were also a particle confined to one dimension, these would be the wave descriptions of the particle. And we see that the energies of the particle are quantized. It can only have energy where n is 1, 2, or 3, and no energies in between. So quantization arises simply because of something's acting like a wave. There's nothing mysterious about quantum mechanics in that sense. You can understand quantum mechanics right here. The number of half wavelengths that fit on a string. You cannot have all wavelengths. You can have these multiples of a half wavelength. They are separated by a certain energy. You heard it in the tube. Boo, boo. That's the separation here. That's a different energy. So I have energy states. And I can rewrite this now in terms of the length of the box and that quantum number, n. So this is a wave equation for that standing wave. The amplitude, A, would be the intensity of the wave, how far up and down it were bouncing. And that we know is proportional to probability, amplitude squared, proportional to probability. So when it's a particle, we're already seeing the amplitude squared is going to be related to the probability of finding the particle in that region. So mysterious properties there. So let's look at this quantization on a string. Let's bring the string around to meet itself. And the same kind of principles have to apply. That is, I have to have waves that meet the boundary conditions. I put boundaries on a wave, I get quantization. That is the fundamental statement of quantum mechanics. If an electron or a particle is free in space, it can have any wavelength it wants. Once you put boundaries on a wave, then only certain waves can work in the system. Only certain standing waves. So you go from a free particle, any wavelength I want, to a bounded particle, only certain waves. So if the particle is bounded like this, I'm stuck on a ring. What are the allowed wavelengths in terms of the radius of the circle? And go ahead and talk about this one directly. I'll go into a breakout room. Ryan can start a poll. I will give you the group of 4 so you can think about that. And are you ready to show a result? Goodness, it's getting warm in here today. Is that what we're thinking? Very overwhelming here for B. So let me give you my thinking on that. So we were saying that the wavelengths have to fit along the length L. So when it was a linear string, we found that half a wavelength would work and a full wavelength would work. And we could write them in terms of L. So if we unwrap the circle, the length is 2 pi r. It's the circumference of the circle. But there's one other thing to consider here, and that is only full waves. If this were a straight line, a half wave would work. So I can draw that on there. If it's a straight line, only a half wave would work. If I could get it, if I could get it all the way on there. I'll try again. Here's my pen. I have to go. Helps if I put a dot in the middle, get me there. So a half wave would work on an unwrapped string. But if I bring the string around to meet itself, then actually this is not a good, it's not a fitting wavelength anymore, because when you get around to here, you'd be coming around to one point, but the wave has to continue down. A wave can't go up and then up again. So the first wave that actually works is the full wavelength. So when I get to the end, when I come back to meet it, I'm starting up again. So it's the same condition. You have to fit waves on, but half integer waves don't work. Only full integer waves work. So if only full integer waves work, then lambda has to be a multiple of 2 pi r. The wavelength has to be a multiple of 2 pi r. So any 2 pi times n will work. If phi of x is 0, then phi of x plus 2 pi must be 0 as you go down the string. So any full multiple of the wavelength will work. So, I have to say wavelength. This wavelength L has to be a full wavelength, so a full lambda, and then I can multiply n times it, and I can get to fraction. Wait a minute, have I done that wrong? I should have any full wavelength. My wavelength is 2 pi r. R has to be in there because that's the length. I haven't solved for it exact. No, I've solved for it exactly right. So the length is r. The length has to be multiples n. So I can put the n there and then solve for the lambda in terms of the length, which is now 2 pi r. And I do believe I get to that. It's n times 2 pi r. R is L is lambda 2 pi r n. N times lambda, divide lambda to the other side. And yeah, so n times lambda is 2 pi r over n. Yes, so that works out. Sorry that I'm also asleep this morning, but you can work out that math as well. Let's do this one just quickly. So which bead on a string has the lowest energy? Let's not do that one, because I haven't shown you that yet. Let's go to another property of waves. So another property of waves we saw is this whole idea of I can add waves up, and if I add a bunch of waves, I can make any other waveform that I want. So I could make this function if I add enough waves like this with different wavelengths together. And we saw that when we looked at the Fourier transform. And I say these math things, and we keep showing math equations. On the exam, I always ask you things more like Chem Quizzes. There aren't going to be any Fourier transforms. There isn't going to be any complicated math. You have to understand this math in terms of the pictures that I'm showing you, the conceptual nature of the math. So there might be a little bit more math in the homework to get you thinking about it, but I'm not going to ask you to do any kind of wave calculations on an exam. This is just a picture of the Fourier transform and a picture of adding waves together. So what I'm doing here is I want to get a function that looks like this. In fact, let me make it slightly different. I want to get a function that looks like this in some region of space. So I have, instead of a long train, if I look just here in this region of space, I have a tight wave, and I can make that tighter and tighter and tighter the more waves I add. So what this is showing you is the number of waves I have to add together at different wavelengths to get to a constrained picture. So more waves gives me more constrained, and I can even start to squeeze this together and get a very constrained wave if I keep adding more wavelengths. So add a bunch of waves together, and I can constrain my wave. That's the only thing I wanted to, that's the take-home lesson, this picture. So if you think about how that, and that's just a property of waves. There's no matter, there's no quantum mechanics in there. That's simply a property of waves. But if waves do that, that implies something about the nature of a matter wave. So if you have one wavelength, you know the momentum exactly. So I know the momentum exactly because it's related to the wavelength. Lambda is h over the momentum. So this is a fixed wave like this. One wavelength, one momentum. But if you ask where is the particle? Remember, that's proportional to the amplitude squared. And the amplitude squared is the same all along this. So you have an equal squared amplitude along this whole region. So if you know the wavelength, you don't know much about the position because there's equal squared amplitude along this whole thing. But if you have lots of waves you can use, so I know the momentum, I have a known mass, and I have a known lambda. I don't know much about the position. I don't have a fixed position. If you're allowed to add lots of wavelengths together, then you can get something that looks like this. If you can add a lot of wavelengths, you can get this wave function. And this wave function, the amplitude squared, is very high right here. So now there's a high probability of finding the particle here because I added a lot of wavelengths. But a lot of wavelengths means you don't know what the energy is. You don't know what the momentum is exactly because you're saying, I'm going to take a lot of different wavelengths. So if I take a lot of different wavelengths, though, I can constrain the position, but I lose my information about the momentum. If I take one momentum, I lose my information about the position. So these things, the certainty, how much I know about the momentum, is related to how much I know about the position. The more I know about the position, that is here it is, the more I know about the position, the less I know about the momentum. So those things are balanced in an inverse proportion. Here I know the momentum more or less exactly, but I have no idea where the particle is on the top. Here, I know where the particle is, but I have to use a zillion different momenta to get to there. So those two things, because it's a wave, have that property. And again, that's not a mysterious property of waves. It would be mysterious about matter. But if waves are going to behave like, if matter is going to behave like a wave, then it has to have these mysterious properties too, or at least you'd expect it to have those mysterious properties. And it turns out it does. So matter has this strange property where if I look very closely and I try to say, is the particle in this tiny position in space right here, I lose track of its exact momentum. I lose track of how fast it's moving back and forth. If I look at a big range, so I say, well, I don't care exactly where it is, then I can measure its energy exactly or more closely. There's an uncertainty in both of them. And oops, I don't have to go anywhere. The interesting thing is that is just a property of waves. And it applies to matter if matter behaves like a wave. So let's talk about this. So you have a wave-like particle passing through a single slit, and you know, single slit, it just, a wave would spread out. There'd be diffraction. It's a single slit, so you don't get interference, you just get diffraction. The question is, if I narrow the slit, what happens to that diffraction pattern? Does it stay the same? Does it spread out? Does it get more narrow? So think about that for a second. Actually, go ahead and talk about it amongst yourselves for a minute and see if you're making that connection. I'll just go to the group of 4. We'll just take one vote on this. Go ahead and talk amongst yourselves about this. We'll take a single vote. And then I'll tell you what I'm thinking. Are you ready to go to your source, Ryan? So looking at your answers here, you're split between A and C. Yeah, so you're telling me, well, it either gets bigger or smaller, and I don't know which. Not a lot of stays the same there. I agree it probably won't stay the same, but let's just talk about this one. So we have this idea here that I have a slit. That means right here, I'm constraining the position. So when I constrain the position there, I change that constraint on the position. I make this smaller. Then the momenta I know less about. So the momenta in the x direction, I don't know less about if I make this smaller. So it could be small momenta, big momenta in the x direction. But the smaller the slit goes, the less I know about it, the more spread that momentum will have. So narrowing the slit says I know a lot more about where it is there. Delta x gets smaller, but delta p must get bigger. So the momenta are different, and by the time the particles get here, they will have spread out more because there's a greater range in momenta. So that is the uncertainty principle that applies to matter because it applies to waves. So here I've written out the wave functions in a slightly different way. So we found that this was the wave function for standing waves in the box. And this is what I was going to show you in that animation earlier, that one standing wave, or half a standing wave, a full standing wave, 1.5 standing waves, and 2 standing waves. Those are the ones that fit in the box or fit along length L. So we're now going to say, well, okay, that's a wave function. I've written the amplitude down. And I'm writing now the various values of n that describe these standing waves. So I let n be 1, and I get a single half wave. I let n be 2, I get a full standing wave. I let n be 3, 1.5. I let n equal 4, and I get 2 full standing waves. We're saying that if I know something about the wave function, the amplitude squared, the square of the wave function, tells me something about the position of the particle, the probability of the particle being in that region of space. So I have high amplitude in this region here in the first wave function, high amplitude in the middle. The particle is more likely to be found in the middle. As I go up, the square of the wave function changes, and you can see, well, now I have the position, well, more likely here and here. I go up, now likely here, here, and here. I go up, more likely here, here, and here. So you can see the range of positions is changing. Relatively narrow, constrained position here, but you go to a higher energy, and I'm likely to find it spread out in the box. And that's a result of the uncertainty principle. I'm going to higher energy, so I'm going to less certainty in the position, spreading out as I go to higher energy, constraining the momentum. So I've written down the amplitude here. Now from the amplitude, I'm not going to go through the calculation, but from the amplitude and the length of the box and the mass of the particle, I can actually assign an energy to each of these, a relative energy to each of these. So we won't go through the calculation. I'll just tell you, I can write down the energy of each state n, and I think you know it's a function of n, higher energy, and it goes as n squared. So if this energy is 1, then the energy of the second level is 4 relative to that. The third one is 9 times that, because I'm going to go up as the square of this quantum number n. And the rest of the things are the length of the box. We're going to fix that for this case. The mass of the particle, that would be fixed, and h squared and 8. So in terms of just the quantum number, you have energy increasing as the square of the quantum number. You have energy in terms of the mass. So higher massive particle, these energy levels would contract. You have it being proportional to the square of the length. That's what I was trying to show you in that animation. When I made the length longer, the energy level spacing went down. So we have an understanding of constraining a particle gives it certain allowed wavelengths. Those allowed wavelengths have energy that are related to the quantum number of the state, the length of the box, and the mass of the particle. So that is all of quantum mechanics in pictures. We're not going to do anything more complicated than that. We have to go, this is 1 dimension, we have to go into 3 dimensions because an electron around an atom is where we're going for, and that's in 3 dimensions. But all these principles apply. We're just going to keep applying them to more complicated systems. But all we have to do is go from 1 dimension to 3. And it turns out we're just going to pick up an extra quantum number for every dimension. So by the time we get to 3, dimensions will have 3 quantum numbers instead of 1. But there'll be relationships between them, and we'll understand how 3-dimensional matter is quantized and their energy levels. I'm going to take a couple extra minutes. We started so late here. I'll chat for a little while. It's Tuesday anyway. That's where this is all recorded. I'll go back and pick up the recording. But I'll just go a little further here. So I've listed quantum numbers. I want to show you the number of nodes, and we saw nodes on the wave when we did the rope. They're the places where the wave function goes to 0. So I have 0 nodes here. The ends of the box don't count as nodes. Those are the boundary conditions. Only zeros within the length of the box count as nodes, where the wave function goes to 0. So I have no nodes here at the lowest level, then 1 in the center at quantum level 2. I have 2 nodes at quantum level 3. I have 3 nodes at quantum level 4. And you can already see a pattern there that the number of nodes, the number of crossings, is linear related to the quantum number. In fact, it's just the quantum number minus 1. So n minus 1 tells me how many nodes are there. You also notice that the number of nodes correlates with the energy, because n going up means energy is going up, and nodes go up with n. So these are higher energy, more nodes. So those are factors of the wavelength, factors of standing waves that lead to quantization. So this now is going to be, I hope, pretty straightforward. If I have to go from one quantum level, one standing wave, to another standing wave, I have to absorb energy somehow. I have to get some energy, but not any old energy. I have to get the exact energy to go from state 1 to state 2. Absorbing other energies doesn't help, because those would correspond to a state that's not allowed. So in order to go from one state to the next, I have to absorb that much energy, that quantum of energy. So the question is, which of these transitions, going from n equal 1 to n equal 2, from n equal 2 to n equal 3, or from n equal 3 to n equal 1, requires the greatest amount of energy? So the highest energy photon to promote matter from one level to the next level. So think about that, chat about that for a minute. We'll start a poll, and I will go to the group of 4. So you have the energy relationship, and start a poll. And got a poll started, and can you display the group of 4 too? So when we go to you, they'll see that. So we're just gonna do a quick check-in on this one. So go ahead, take a quick vote. And I'm gonna go through what that is there. That's about 80 of you still hanging with us. All right, Ryan, let's see what those 80 on just a really quick poll think. So I didn't give you much time to think, but you're converging to B. So I will take control of the screen back. And I think you're saying, and you're saying correctly, that the amount of energy, the energy difference between any two states, is the energy of the final minus the energy of the initial. So the energy of the final state, state 2, is n squared times the energy relationship. The initial state, the initial state 1, is the that n squared. So if it's n squared minus n squared, so the final state is 2 here, so that's 4 squared minus 1 squared. So that would give you 3 here. So if I have n equal 2 going to n equal 1, I have to square those two things. So that's 4 minus 1. So that's 3 energy units. If I go 3 to 2, then I have 3 squared minus 2 squared. Then I have 9 minus 4 is relative energy 5 energy units. So that's a bigger absorption. C is a bigger energy split, but it's not an absorption, it's an emission. I'm going down in energy. So the first one, that's an absorption going from 1 to 2, going from 2 to 3 is more energy. On that plot, I didn't draw the correct spacing because I needed you to think about that for a second. But can you go back to the group of 4 just a second, Ryan? Are you there? I'll go to Ryan's screen. That energy spacing is reflected here. So here's the correct energy spacing as a function of n. And now you can see it more clearly that if I'm going to go from energy state 1 to 2, that's that much energy. If I'm going to go from 1 to 3, n equal 1 to n equal 3, that's bigger energy. If I was going to go from n equal 1 to n equal 4, more energy, and it's not linear, it's going as the square. So when we did those two absorptions, we said, well, 2 to 3 is one I'm interested in. 2 to 3 is much bigger than 1 to 2. 1 to 3 is very big, but we're saying 3 to 1. And it's a bigger energy difference, but I asked for an absorption, and coming down would be an emission of energy. So I just want to summarize that and have you think about it. So transitions between energy levels require an absorption of energy equal to the energy difference between those two states. That energy difference has to be taken in chunks, so it has to be taken in photon chunks. So how do I get from, oops, I went back and I hit the annotation. So if I want to get from here to here, that's a specific amount of energy, final minus initial. If I'm going to absorb a photon to do it, then I need to find a h nu that has that energy difference, that amount of energy. So we can look at photons just doing that. These are electronic transitions now. If I bring in a photon in the purple range, and I'm saying that's in the ultraviolet range in this case, that photon has no effect on the system, passes right through because there isn't an energy spacing that's equal to that photon energy. I didn't tell you what it was, but I'm saying that one didn't match any of these differences. If you have one that matches one of the differences, then that will be absorbed by the system. The system will go from, in this case, the ground state, the lowest energy state, to our highest energy state. And if that happened, you would see an absorption of that energy. That energy would be absorbed from your full spectrum. So this is a line spectrum, as we talked about earlier. An individual amount of energy is absorbed, disappears from the spectrum because it's absorbed by this system. This system could be an atom. Here's another wavelength, green, but that one is appropriate in energy for this transition. So that energy would also be absorbed. And there was a yellow, but there were no spacings appropriate for that photon. So here's a photon in the red, and there is an energy, this energy here, appropriate for that amount of photon energy, so that is absorbed as well. And I can do the reverse. If the system already has energy, then it can drop down from high energy to low energy. And in that case, there'd be an emission of energy, but one specific photon energy. So dropping from this second to the first energy level, from the second to the ground state, the first excited state to the ground state, that would emit this same color of red, but it's an emission, so you'd see a single emission line. You're not putting in energy anymore, you're just observing what's happening. So there's no spectrum. This is absorption. There's no spectrum here. You're just looking at which wavelengths are emitted. And of course, you'd see the green photon being emitted in your line spectrum, and you'd see the same blue photon being emitted in that spectrum. So we'll pick up here tomorrow, and we'll do a few chem quizzes related to this. Right now, if there are any questions, you can give me some questions. Again, I apologize for this. Oh, poo, we're supposed to show them prism. Let's show it to them. If you're still here, we're going to demonstrate this prism that you're going to look at. We're going to give Ryan a second to look at that. She's bringing it up on her screen. When you're ready, Ryan, I'll show it on this one. She's ready. So Ryan's going to have to do the actual mouse clicks, but I just want to show you the idea here. So when you do your homework now, the assignments on B courses are going to open this window. The first time you do it, you have to register to use the Prism software, but it'll take you to the Prism page. You enter your username. It'll know what that is. And you enter the code, the access code that you got at the bookstore. That will open this software up for you. When you're in that software, these assessments, notice there's 4 panels, a video, a text, a graphic, and an assessment window. Your assessments you'll do here now. So assessments are essentially your homework questions. You'll do them here. So Ryan, if you'll do a mouse click, just answer this question. How many protons in the nucleus of a helium atom? Let's see if Ryan can get that right. She had that set up and we were logged out for too long. So actually you guys should not have to do this step. If you start at B courses, it will always have you logged in. So we'll wait for that to load. Yep. Go to the 4-panel mode. She's gonna start an assignment and go to the 4-panel mode. So here's the assessment. She went through the steps of going to the assignments in B courses, clicking on the assignment. This panel opened. She had to re-log in. And now she has the 4 panels. She's gonna answer this question. So go ahead, how many protons in the nucleus of a helium atom? So Ryan's going to take a stab at that. She got that right, and you can see you've completed this portion of the assignment. You have to answer 3 correctly, but you can page through them. So Ryan, if you just page through to the next one, there's another question. Go ahead, page through another one. We're not going to do that one. We're going to skip this one. That one I already did, so it showed you. You've already answered that one correctly. So you have to answer 3 correctly, and we were doing them earlier, so we've answered that one. We answered with you watching was the 3rd one. So once you answer 3 correctly, you're done. But this software, the way it works is it has these sync buttons. So if you press the sync in your assessment window, it brings all the other windows. Can you page through? You might not be able to run that video. You have to be logged in with your CalNet ID on YouTube to run these videos. So here's a video also explaining this. So you have a chalkboard, a bit of text, and a video helping you do this question. So you get this synchronization of different media to help you do this. You can browse through any panel. So why don't you browse here a couple panels. So we've gone to different text here. Say we like that description, we can sync this window and it'll bring up videos and graphics that go along with this text. You notice when we hit sync there, it did not change the assessment window. That's because we had sync locked here. We can unlock sync here. Submit that assessment.
You can do it on the website, but no, it's right now we're in assignments. You can do it if you're just in the table of contents or just in the 4-panel view, but while you're in assignments.
Okay, so browse away from assignments, go to the 4-panel view in general. You can use this when you're not doing your assignments. If you just type in a word here, stop there, Ryan. Oops, try again. Type in, start typing in the word. Stop there. So this is a search window, but it's a search on only certain terms. It's like you're looking at the index of a textbook. So she started to type mole. You can put your E in there. Type the whole word mole. And you can see these are the things that have that text string in them. Mole was what you're interested in, so you can click on mole. And then the graphics will sync. And if you page this up, you can see a definition of mole. You can see that discussion we did in lecture, how many mole of dollars, and a graphic that relates to that. You can start the video. And now this is unlocked. They're all unlocked, so you can browse through any one of them. So let's browse through the lecture videos. So mole defined there. We'll browse a little bit more. Go ahead, keep browsing. Actually, it's easier to browse through text because you can see it. Browse through text. So here I'm going to talk about balancing equations and molecules. It's related to the mole. Let's say I'm interested in that. I can sync the text with sync the other windows to that text. So this will give you a new assessment and a new graphic and a new video related to that concept. And at any time, now say you're interested in this assessment, I can lock that panel and browse through somewhere else. So let's browse through graphics. I can browse through graphics till I find something that's interesting that I think might help me with that. So a couple browsers there, say that one helps me with that. Then sync the rest of the panels. And that'll bring up text and video associated with that graphic. So the idea here is you have small chunks of content but they're correlated with each other. So you can look at bits of content that are related to what you're thinking about right there. You're not going through a whole textbook. You're essentially going through kind of an automated index. You've got an idea of what you want to know, and the other stuff is close by. It's going to get that information for you in the different panels. So that's how Prism works. We're working on it furiously to keep it up and running and have the right content in there for you. So go ahead, register today, start playing with that. As this, you'll see your assignments in your B courses have changed to Prism assignments from B courses assignments, but you still click on the assessments and you do the same, essentially they're the same questions, except they appear in this window. Read the instructions, there's instructions online. Read about how many assessments you need to do. Read everything first, go to your B courses. Can you go to home on the B courses? If you go to the syllabus, you have information on the Prism guide and the course information. So here's how to use Prism. If you go back to the home page for us, or back to the syllabus for us, if you click on the course information tells you about how the homework works, the Prism software and the homework. Keep paging down if you can. Here it is, Prism software and working on homework is on the website. So look at those things first. Play with it, learn how to do it, especially before you start asking questions that are covered here. Okay, thanks, Ryan. That was cool.
Do you want to, while we're here, talk about SLC?
Sure. Did you set up a new page? The SLC, that's the Student Learning Center. That's independent of the class. There's no relationship between those. They are tutors free to you, standing by more or less, to help you with chemistry. They're a function of the university, essentially. University supports the Student Learning Center. And they'll help you with any of your courses. You're taking chemistry right now. So there's some information on, if you, doesn't it go to the SLC website right now if you do that? Yeah. So here's the SLC website, and you can get information on how to get that help and where to find them. So that's it for today. We went over, we started late, sorry about that. We'll pick up tomorrow. Hold your questions till then, and we'll give you more time to interact and ask questions tomorrow. All right, take care, guys.